Hello everyone, welcome to the video lecture series of operating system. In today's session, we are going to start one new topic which is nothing but input-output management and disk scheduling. Specifically, we are going to start input-output management first in this particular session. Myself, Kunal Panchal, your instructor. In input-output management, we are going to start the first topic, which is nothing but input-output buffering. So before going to jump into the input-output buffering with respect to I/O management, first of all we need to understand what is buffer, then what is buffering, and then we will discuss what is I/O buffering. So what is buffer? So buffer is basically used to store the data for a temporary purpose. Fine. Suppose if you want to do arithmetic calculations, and if you want to store the result of that calculation for a while, so you can store the data into a buffer for a while, so that you can after some time you can use that value for further calculation. So for buffer is nothing but temporary storage. And what is buffering? So buffering is nothing but one technique through which we are using the functionality of buffer. Okay. And now what is I/O buffering? I/O stands for input-output buffering. Fine. So when we are talking about I/O devices, as you know very well, input-output devices are very slow as compared to CPU and memory, because CPU and memory are digital devices and they are very fast as compared to input-output devices. So that is the reason why we need to have one concept of buffering with respect to I/O management or with respect to input-output devices, because to overcome the problem of data loss, okay, to overcome the problem of, you can say, coordination up to certain extent. So if you maintain a coordination between these two incompatible devices, like one is memory and CPU devices, and other end we have I/O devices. If these two devices which are not compatible with each other in terms of processing speed, if you want to make coordination between such type of devices, in that case buffering mechanism we need to use, or buffering technique we need to use. So let us discuss I/O buffering in detail. So when we are talking about multi-programming operating system, in which as you know very well, more than one process are ready for execution in main memory, and processes are having two types. Some of processes can be CPU bound processes, or it can be I/O bound processes. CPU bound processes can perform its task on CPU, and I/O bound processes can perform its task on I/O devices only. Fine. So then day by day, when number of processes, like in multi-programming operating system, or in multitasking, or we say time sharing operating system, day by day the number of processes are increasing in main memory, because the size of the main memory is increasing gradually. So what will happen if number of processes are increasing? Definitely the number of input-output, or number of I/O bound processes can be increased in main memory, which are waiting to execute a task on I/O devices. So in this case, if more and more number of I/O bound processes we have in main memory which are ready for execution, so as you know very well, by having a single processor, okay, or a dedicated processor, we can execute only one process at a time. So what will happen when multiple requests arrive at the same time? So in that case, for some period of time, we can store that upcoming request in one temporary storage. That storage is nothing but buffer. Okay. So let us discuss IO buffering. So suppose that a user process, as I told you, wishes to read a block of data from a disk. So one user process is entered into a system. So it means what, now it is waiting in main memory, and that process wants to read data from the disk. It means what, this is the IO process, as I told you earlier. Yes. The simplest way would be to execute an IO command to the disk unit and then wait for the data to become available. That is the simplest way. Means what, IO bound process entered into main memory, and that process will wait until it gets chance to execute on the IO devices. Until that time, it will be in a blocking state or waiting state. So this is the simplest way of execution. But this, we can say, this approach is not appropriate approach in current scenario. Fine. So the waiting, this, if you are following this approach, the waiting would be either busy waiting continuously, okay, or more practically we can say process suspension on an interrupt. If process has to wait for a long period of time, process can be suspended when an interrupt is occurred. So such type of problems can be there. Fine. So to avoid this problem, to avoid this overhead, or we can say inefficient. This is inefficient approach. Yes, because we are waiting for the IO devices, and IO devices are not available for a long period of time. So we are doing busy waiting for a long period of time, and we are not getting the IO devices. So this approach is inefficient approach. So to avoid this inefficiency, it is sometimes convenient to perform input transfer in advance of request being made, and to perform output transfers sometimes after the request is made. This technique is known as buffering. Means what we can do is, instead of doing such type of thing, what we can do is, we can when some of the processes, when IO bound processes are not that much in main memory for execution, in that case what we will do, we will process that IO bound request and store that request into a buffer, so that, and what we need to do is, we need to priorly, means if such type of a process come into the existence, what we can do is, we can priorly store that data in such type of request into a IO buffer, so that later we can accommodate more number of processes in main memory. So this technique is nothing but buffering. So it means what, it provides coordination between memory and IO devices. How? Let us discuss in detail as far as buffering is concerned. So what is buffering? Let us discuss a little in depth. So buffering is a technique, as I told you earlier in the first slide. Buffering is a technique by which the device manager can keep slower IO devices busy. It's a technique through which the device manager can keep slower IO devices busy by transferring the data in advance. During times when a process is not requesting IO operations. It means buffering is a technique through which we can achieve coordination, and it is efficient technique as compared to the without buffering technique or strategy. Fine. So what we'll do, we will do the advanced data transfer during times when a process is not requesting or not requiring IO operations. At that time, if process is working on CPU, at that time we will transfer in advance the IO bound data, information into this buffer, so that later on we can execute that task on IO devices. So this is called buffering. Now there are different types of buffering schemes we have in IO management or input output management. One is no buffering, second one is single buffering technique, third one is double buffering technique, and fourth one is circular buffering technique. Okay, so these four techniques we need to discuss in detail. So let us start with no buffering first. So in the case of no buffering, you can see in this particular figure, the name implies no buffering means what? We are using traditional approach without using any buffer. Okay, whenever the requirement come into the existence, we will fetch that data from the IO device and give it to the user process. Means without a buffer, the operating system directly accesses the device when it needs. Means when user process requests IO devices for its own execution, at runtime, operating system will provide the IO devices to the user process on demand. Means there are chances in this case waiting can be very long. So it is inefficient approach, because if IO devices is easy at that time, so we need to wait to get the IO devices anyhow. There is no other option. We cannot store that user request for a while and later on we can execute on the IO devices. We do not, because in this case there is no buffer in main memory. So this is not an efficient approach. So to increase the efficiency, let us discuss the second technique, which is nothing but single buffering technique. So in the case of single buffering, instead of having null buffer, in this case we have a single buffer in main memory. So in this case, operating systems assigns a buffer in main memory for an IO request. So because we are talking about IO buffering, so definitely this buffer is dedicated for IO operations only. Yes. So in this case, what will happen in single buffering, when user process demands to access an input output device, at that time, what will happen? The operating system will take the control and try to get the input output devices and give it to the user process. But in this case, if IO device is at that time busy, so what we can do is we can fetch or we can say what we can do is, in this case, user request or user process can be stored for a while in main memory, specifically in buffer. Okay, and later on it can be executed on the IO devices. So what is the advantage? So once the IO device is busy, at that time we can store that request for a while, in main memory, so that other user process which requires IO device can send a request to the operating system to access the IO devices. But in this case, there is a problem, because we are talking about single buffering. So it means what? In this case, the IO device provides the IO operation. So it means what? It is in operation, and once it is included into the buffer, then the user process will fetch that data from the buffer. So that operation we can call as move operation. So there is in and move, two types of operations we have. It means what? One is inserting and one is deleting something from this. So it means what? This is one type of critical section problem we can say. If you recall, in the case of producer-consumer problem, okay, the producer can produce something at a particular moment of time, but at the same time, consumer cannot consume something. So it means what? At the same time, two operations cannot be performed. At the same time, either in operation can be performed or new operation can be performed, but both the operations cannot perform simultaneously because we have a single buffer in this case. So while inserting something, we cannot delete at the same time. Fine. So this is kind of producer consumer. So input output is in operation is nothing but we are producing something, and move means what? We are consuming something. So there is one problem in this case. The synchronization should be there. Coordination or synchronization should be there between these two atomic operations. So in and move is nothing but atomic operation in this case. Fine. So there is one limitation. We can do only one operation at a time in this case, and we can not achieve more level of efficiency by having single buffering strategy. So there is one limitation in this case. So to solve this problem of critical section, like at a particular moment of time only one operation can be performed. To solve this problem, we have another technique called double buffering. In this case, instead of one, we have two buffers in main memory. So in this case, use two system buffers instead of one. A process can transfer data to or from one buffer while the operating system empties or fills the other buffers. So it is also known as buffer swapping. Means what will happen in this case? In this case, there is no concept of critical section. That problem we have resolved because instead of one, we have two buffer in main memory. So any of the buffer can be used to insert the data, okay, and any of the buffer can be used to delete something or move something from the buffer. So it means what? Suppose out of two, first buffer is used to insert something, so second buffer would be used for delete something in it. Okay, from it. Fine. So the coordination can be easily maintained in this case. Why? Because we have two buffer and one buffer is dedicated for in operation and another buffer is dedicated for move operation. So in this case, we can solve the problem of single buffering strategy, but there is one problem in this case also. It is not that much efficient because we have only two buffers. Okay, so at a time we can perform two operations, not more than that. Fine. So this is the limitation of double buffering strategy. So to resolve this problem, we have multiple message buffer or circular buffer strategy. So circular buffer strategy is also known as multiple message buffering strategy as well. So in this case, two or more buffers are used in main memory. So each individual buffer is one unit in a circular buffer. Each individual buffer is one unit in a circular buffer. Okay. Used when IO operations must keep up with the process. Means in this case, what will happen? We have multiple buffers. Okay, and multiple buffers can arrange in a circular fashion. So the in operation and move operation can be performed in a circular fashion. Means one element is inserted, for example. Okay, one request or element we can say in this case, if you consider one element is inserted in particular buffer, then that buffer will be moved down and the last buffer will come up. And the second element will be inserted into the recently inserted the buffer, and the out operation or move operation will be performed when the very first buffer is reached to the nth place. That from the nth place the move operation can be performed, and at the first place the insertion operation can be performed. And in this way, in circular fashion, these data transfer operation can be performed, or we can say input output request would be satisfied. So in this case, we can accommodate more number of requests. Okay, so definitely this approach is more efficient as compared to the previous techniques that we have discussed. Right? So this is all about buffering techniques, specifically IO buffering, right? With respect to input-output management. So I hope this was clear to you. Thanks for watching this video. See you in the next one.